Eso lo di a Gustavo. Gustavo tiene.
¿Te acuerdas que teníamos una serie
Bueno, pero eso es lo que tú dices. Yo no necesito eso para mis códigos que funcionan. Pero ese código sí te hace falta. O sea,
se presenta también como build dynamic library, ya no está.
It's your last talk.
Entonces, esta modificación y no
sí, ese es el viejo, ¿no? Eso no puede ser ningún problema.
Okay, let's start. This is the last talk of Peter. So, pay attention, please.
Okay, so let's start. So, part 4, it's going to be, again, like yesterday, a bit more detailed on some examples and so on. And it's going to do looking at more on larger structure marks with HODs, because until now I'm looking more at large structure marks from galaxy formation models. I just have a contrast in them a bit. And some discussion about HODs and so on in here, and how there are things which you need to think about when doing this. So I will do a short case study at some level. It's the large structure marks from MXXL for DESI BGS. So it's a DESI Bright Galaxy Survey. Then constructing HODs, possibly shams, using symmetric galaxy formation models. And then if there is some time, I'll give some words about the project and so on, and maybe people have a question about it. Mostly because I'm not going to be around this afternoon when the project is going to be discussed, so if you have a question, you might be worth asking them. But one short slide about DESI, the Bright Galaxy Survey, and give you some numbers in it for it, and it's like a 14,000 square degree survey, which is planned to start in 2019. Yeah, it's just to give an idea of, I've been mentioning gamma quite regularly, and so on. It's 60 times larger than gamma, so significant large cosmological volume, and depth about 19.5 in the R band, so it's slightly shallower than gamma. But what's nice with this is actually a survey that you actually have something already for. Gamma gives you a baseline of the information that you will predict for BGS survey. So in one sense, if you have a small survey with all the information in and so on, you can actually do a very good job on hopefully getting an HOD model for the BGS survey. And I contrast this in the case of other DESI surveys which are focused on ELGs, LRGs, or quasars. We don't have as much information for some of these tracers, so therefore it's much harder to actually create something which is realistic and very accurate at this stage. Lots of work is going on this, and this is where we actually have to work. So anyhow, this is the BGS number. The main science goal, like all the DESI surveys, is BAOs, accurate measurement of bioacoustic oscillation scale, RSD, radius space distortions to measure growth rates. But basically, both of these main science goals require you to have large volumes to work with. So any other things I talked about yesterday with the type of galaxy formation model and simulation used there, it's not adequate for these type of science goals. They're great, those 5 megaparsec boxes for doing galaxy formation on, but not for BAOs and RSD measurements in that sense. They are limited that. So there's a need for large survey marks now in the case of BGS to test the survey systematics, because not all objects will be observed, so you need to have a mark that you can actually test this for. To prepare and test analysis pipelines, you want to have to figure out how you can do the survey. Provide insight on service strategy, and that's actually quite important in the case of the DESI Bright Galaxy Survey, because it's not done on its own right. It's actually coupled, BGS is coupled with the Milky Way survey of bright stars. So the choices are therefore that you're in one sense, if I rephrase like this, BGS, the success rate of observing a galaxy will depend to some extent what is around it, which might be stars, which are not part of your main science, and therefore there's a coupling there. So that's kind of like the needs. So then let me explain the simulation used for this. It's the MXXL simulation, which was done in 2010. It's 300 billion particles in a 3 gigaparsec box. So in its days was one of the largest done. It's a mass resolution of 6.2 10 to the 9 in solar masses, H inverse solar masses for the particles, and has the W map 1 cosmology, and is described in Angolo et al. 2012. Okay. So just to give you an idea, MXXL is not suitable for GALForm or Galaxy Information Models I explained before. It's because it has too low mass resolution. In an instance like with mass of the particle 6 × 10⁹, you're just below the threshold of being able to resolve enough small mass halos of the order smaller than 10⁻11, so that you can't actually have full build-up of the Galaxy Information merger trace properly. What we discussed yesterday, that you have all the information is not a perfect light cone, but it's actually ideal for BAO studies because of its volume. Yeah, it's very, very large volume and so on. Now, I just want to contrast this with RTRIM and MXXL. So RTRIM has 3 times higher mass resolution, so actually becomes just about perfect to be able to do Galaxy Information Model on it. Just about perfect in that sense. It has twice the number of snapshots, so it's actually even better in the terms of resolution of the time stepping and so on for light cone purposes, and has a better cosmology because this RTRIM was done in WMAP7, whereas this one was done in WMAP1 cosmology, and that's for consistency part with other simulations to be able to do studies of what you do in different sizes of simulations. So clearly the work I present now would be the natural thing to do is to develop it to do it on RTRIM. Yeah. Unfortunately, a man who has RTRIM has just disappeared from the room, so he hasn't heard my plea, but hopefully he will come back and hear my plea later on again. I won't forget about it. Anyway, so MXXL HOD light cone. So first of all, we create an HOD-based light cone for DESI, yeah? And with the focus being Bright Galaxy Survey. Now, why do I say what the focus is? Because you need to resolve and what is needed. It's not here, MXXL, the snapshot information only, you need to interpolation. Here we have actually a distribution of when you use the interpolation on the light cones, you get your halo light cone, and all of this is actually now, this is the dark matter density field actually, which has been interpolated between redshift 0 and redshift 1. You have loads of snapshots coming up here, so you don't see any longer, there is discrete steps and so on. And once you have your halo light cone, and the halo light cone is following exactly the same scheme as described yesterday during lectures, meaning how do you interpolate the center of galaxies in one sense, the cubic spline interpolation, which works pretty well in that sense. Now you have a halo, you have a light cone which have halos along the line of sight. Okay, then that should be straightforward. We all know how to populate HODs because we followed Aldo's lecture, so what am I talking about? There's a couple of more things you haven't thought about there. First of all, halo masses need to be interpolated now, because whenever in my light cone, and looking at all the halos that are above 10⁻13 in solar mass, that gives me the black line up here, you can see these jumps coming in, and it becomes even more apparent for the 10⁻14 halo, the biggest halos. The reason you have these discrete jumps, is because that's where the snapshots appears. So all these halos have a fixed number density because they're not going to come in being evolved. They won't accrete any mass because you view them at a fixed time. So again, you need to actually account for that to create an interpolated halo masses. HOD models are generally not nested. So if I ask the HOD for L-star galaxies, and I find what it is for galaxies brighter than L-star, and I have a requirement and I find a HOD, there's no implicit assumption that it should satisfy the constraint I get for galaxy which are 2 times L-star, for example. So let's give an example. Assume I did my fit for the sample which is greater than 2 L-star, and I find that there is 10 to the minus, there's a 1 in 100 halo at 10 to the 12 solar masses. Yes, I take up that number out of my head. Yeah. There's no requirement for my sample which is brighter, with a fainter, which contain all the 2 L-star galaxies, to at least have 1 in 100 galaxies, 1 in 100 halos at that halo mass being populated. Because they're not nested, they're not talking to each other. Yeah. You could do it, but that's not what people do. Yeah. So is this non-nesting a problem? Yeah, that they are not knowing it is? Because if you want to create a mark using the HOD model, and you want to want one mark with galaxy properties for the whole sample, that will be an issue. Because you have actually decided that some objects should exist in some halos, and if they are looking at a brighter sample or a fainter sample now, fainter limited sample, there is not enough objects in there. No, that's not a problem if you want to mark for a specific HUD sample, just a fixed redshift, just these ones, and just give you an object with positions, R8 Decan redshift, or XYZ. This doesn't matter, because my object doesn't have any properties. But if I assign properties to my model, then it matters. I just want to make sure that there are some HUD model fits are nested, but actually very rarely, because increased correlation between samples, which is hard to estimate. Because I have a model to predict how well I do it. Now, if I need to know to do that fit how the other samples are doing, the brighter samples, they are all correlated, and that's going to be very hard to implement because you need to know the covariances again for these samples. So that's something we need to remember on these ones. So in order to do this to some level, what was done here, so this is actually work done by Alex Smith in Durham, PhD student of Sean Call, and so they have encountered all of these small things coming up, because what's important is that you do then a smooth function with luminosity for your HUD parameters. Yeah, and when doing this smooth function, what you see, you can actually then give this the fits here, which is a solid line, and the intrinsic version of the HUD fit done by Zheng and so on. You can see that they differ to some extent. Yeah. That is by construction, because here we need to in 1 in 100 or less than 1 in 10 chance. Yeah. However, if you look at these fits here, the original fits, the dashed ones here, they cross each other. That's an example of crossing. So this tells me that this sample here, this red one, which is minus 21.5, has actually more objects in it in these halos than the sample which are minus 21, which is actually contains this one. So this is what I mean by this nesting problem. They're actually, in one sense, incompatible with each other. Yeah. So that has been accounted for by forcing the fits being to be actually have so it's the model, HUD model hasn't been changed as it should have been done, but here they actually done an approximation of forcing the HUD fit such a way that it's actually going to go down quicker and making sure that it's consistent. Okay, that's fine. Now I have my HUD at a given redshift, and because I constrained it from data using SDSS, that's great. Now, evolution of HUD with redshift. So in the light cone, the underlying dark matter density evolves, because the halos evolves, and that's what we had because we had different snapshots. So that's all good. But if my halos evolve, should I not make some assumption about my HUD? Can I use the same HUD for all at all redshifts? And that's the problem as well. So an intrinsic limitation of the HUD formalism is that it's only meant to provide a statistical description of a given sample, of a given data set. It's not meant to give you the evolution of it. Yeah? So a galaxy formation model, they can provide a framework with evolution. Is it possible to use them as a guide to tell you how the HUD should evolve? Yeah? And I think this is the reminder to this. The initial suggestion of the functional form for HUD models comes actually on with semi-liquid models. Yeah, if you go back to the work in the early 2000s or in late 1990s, you actually see that the chosen model is actually the one which is suggested by semitic models, because they are they are not HUD models. They have, by construction, galaxies in halos, so you can actually plot this HUD from a galaxy formation model. So that's kind of like the reason why it makes sense to actually look at for the evolution as well. Is that something one can do? You know, I'm not going to say it's going to be the answer, but it gives you an insight of what might be relevant. So this is work done by Sergio Contreras, recently posted on our archive. And so we've been looking at the clustering and the HUDs for M-star, stellar mass ranked number densities. Yeah? And I just make sure it's stellar mass ranked number densities, because we're going to come into that later on towards the end of the presentation here. Yeah. And we've just taken a galaxy formation model, the Gonzalez-Perez, and we plotted here the correlation function as function of radius for a series of sample of different number densities. Yeah. So if you have here, the black line has the lowest number density, the highest number density, which means that it actually probably considered the faintest, the smallest galaxies. And this cyan line, which is, or maybe let's look at this magenta line, gives you the lower number densities, which means that you can have bigger objects. And this gives you the correlation function. Yeah. This is the relative correlation function of your samples divided by the one which has the lowest number density. If you had plotted this divided by the dark matter, we actually see the bias. Yeah. I only realized when actually taking this plot into the talk that we have a Broadtest function bias. And where I thought it would be more clever. Anyway, blame authors number 5 here, not reading paper well enough. Anyway, so here we have, this is, you measure this in a simulation. This is, you have that in simulation. You know what the mean number of galaxies per halo is in the simulation for the different number densities. Okay, that's for one model, a redshift 0. Nothing more than that. And just give you an idea that that's the typical thing that you see here, that if you go to the brightest sample, actually you have a threshold which has higher stellar masses. The bigger object, the bigger galaxy living in bigger halos, where the satellites are coming in there in the upturn there. Okay. Now let's look at the evolution of the clustering and HOD in 2 models. The reason I choose 2 models is, you want to be able to make sure that, do you have some general thing coming out, or is this just all peculiar to Galform, the Durham model? Because there is also some limitation on this. So you want to see, can you see trends? So we actually use the Guo et al. Model, the Munich model, and what's nice with that one is the Guo et al. And the Gonzalez-Perez model, they're built on the same underlying dark matter simulation. Different merger trees though, because they're running different merger trees, but it's the same underlying dark matter simulation. And that's kind of useful, because then you can at least say it's not cosmology and so on is going to cause troubles. It's actually the galaxy formation model, what you try to do with it. Now, on the top panel here is shown as function of is the HOD, the halo occupation distribution, as function of halo mass. 4 different samples, and they are being color-coded as function of redshift. Yeah. So this is the highest redshift sample, the redshift 3, and you go down in redshift, and you can see that for this number density, you have a change in the HOD. Yeah. That's for the Gonzalez model. The same thing you can do the same thing here for the Guo model. And you can see the trends are pretty much similar. You change here your transition mass, but in detail they are different. Here you can see the clustering with 2 models, and you can see the clustering is rather different. Yeah. Primarily the difference are on the smaller scales, but actually Gonzalez model is actually quite different. You have a stratification of the clustering here, whereas here they actually seem to be all converging to one part. So that means that likely these models have a very different way of doing dynamical friction or actually merger schemes within the halo. Yeah. So that's what's going to cause these differences. And you don't see very much of a difference on the HOD on this level, because the HOD doesn't tell you where the satellites are. They don't tell you how many you have. Okay, so, and then you're going to use a standard HOD model, which is very much standard here, that you have it's a 5-parameter model, where you have the typical parameters you use for your model is the first of all, the M1, the mass at which you have, on average, 1 satellite galaxy per halo. You have the slope here, alpha. This is the sigma. It gives you an idea of how much how smooth the transition should be on the central terms. And here's you have your central, which just goes in here that all halos are populated with the central. Okay. The reason I'm showing this one is because the HOD will come up at different times, and most importantly is because we want to constrain those parameters of the HOD model. Okay. So evolution of HOD parameters. So going back to this slide here, yeah, you can actually look at these functional form, these HODs, and you can try to fit them with this model. Yeah? And by fitting this model, you get answer what is your different valued parameters. Okay. And you can plot them for the different number densities and as functional redshift. Yeah? So this is M1 we look at here. And what you can see in the Gonzalez model and the Guo model, that first thing we see with redshift, M1 seems to decrease with redshift, which makes sense because you don't have that many big halos. The bigger halo, like halo grow with redshift. So in one sense, as function of time, your halos will grow. So that's, you would expect this one to increase. Yeah. The other thing which is interesting is that both models are very similar in these trends. And they have similar trends as function of number densities as well. Okay? For M min, the minimum mass in which you will put a galaxy in is also kind of similar, but on the highest number density, lowest number densities, there seem to be some differences. Yeah? But otherwise, the trends are pretty similar. So, you know, you might have something generic here, because these are two completely different galaxy formation models, and they have only been tuned to reproduce redshift 0 data. So, you know, there are physics in them, so therefore you would hope that the physics is kind of like making sense. It doesn't need to be right. I'm not saying that they are right in any way, but it's interesting that two different models have similar trends. Okay, for M1 and M min. Now you do the same work with M cut and alpha, the other two parameters. So this for M cut, again, it looks kind of like similar, the trends, whereas alpha is very different for the two models. First look, you think, oh, it looks similar. Actually, no, because they have reversed the order. In the I think this is the Gonzalez model. Yep. In the Gonzalez model, you can see that the order here is going from, and it has been reversed with respect to the color coding here. The order, they're not the same orders. Blue is at the bottom. Here's blue is at the top, and then you have red below. You have red above. You actually change the order. Yeah. So that means they have different trends on how many satellites are occupying the halos with redshift. So the slope, that slope is different. That's less generic, worth keeping in mind, because that means that's something maybe one should be careful about in trying to model this. And this is the same plot again, but last but not least, you have log sigma m, and this one, if you find any trend here, I would like to let you, tell me, but I can't see any trend. It's just all over the place. And that's because log sigma m is actually very hard to constrain. Yeah, it's degenerate with other parameters as well. And that's also something you need to remember when using your HODs is the degeneracies between parameters. Okay, so we found out that the three mass parameters you HOD are kind of generic, you know, but the two other ones, alpha and log sigma m, are less. Now, do we need 5 parameters also all the time? Actually, you can say that one parameter is constrained by using the other one, because you have a constraint on number densities. You know what the number density of a sample is. To some level, that has a constraint on your HOD parameter as well. So, but looking at this, we can try to provide, and this is what we have provided in the dashed lines, some simple fits. They're either linear in these quantities, or they have been broken parallels, like here, flat and then going down. Yeah, that's the two kind of fits we have adopted here. If I use those fits, how does my HOD look like with respect to the actual HOD at redshift 1, which is the black line in black? The fitted HOD, if I took the black HOD here and I try to fit it by using my best HOD, that gives me an idea, that gives me the solid dashed. Where is that one? Pretty much on top of it. So it's a good description of HOD. You have the HOD. That is the one I take. Another thing is that M1 over M min is usually a very interesting parameter to consider when you actually look at HOD models. And that one you can actually plot this function of redshift for the two different models. And the two different models are very different in spread for your different number densities and how it varies. And this solid line is what you actually measure, and in the model, whereas the dashed is when you have this fitted HOD parameter, how it works. And it is actually not bad, actually, in general terms. Possibly not for the magenta line is theirs, but most discrepant. But otherwise seems to be working quite okay. And that's good, because that means that actually you have some input on a parameter which is of interest on how to interpret the HOD. And it would have been much harder to actually find a permutation which works generically here. So our simple model is actually quite practical in that respect. Now, a small digression. So we have these HOD parameters. We have roughly how they evolve and so on. And we are kind of happy with that. I'm just going to make a small digression on talking about the changing membership of stellar mass ranked samples and so on. And this comes down to the fact that I think it depends on how you think about these problems. So assume you have your stellar mass function at redshift 1, which is the magenta line here. Yeah? And you're asking yourself, I select a sample of object, the black histogram. Now, the black histogram is here. Yeah? So first of all, what you see, the histogram has moved. Yeah? But that's normal. Galaxies grow. Yeah? Not a big problem with that. I'm happy with that. But there's two things. If you look at your density on your number density at that redshift, at redshift 0, that number density is here. All of these objects in this part here, which you would not have accounted for initially when you have made your cut of evolving your number density down to redshift 0. And the reason for that is because these are the objects which grows from redshift 1 to redshift 0 to populate this plane here. Yeah. These are the objects which has come in there to actually, they have grown in time and so on. And so that's one of the things. So this kind of model of tracking or fixing number densities is actually, one kind of think initially it's very handy. You can use it for evolutionary studies. But actually, we need to be very careful about that because the fixed number density doesn't mean that you're actually keeping track of the same objects. There's actually a large fraction of objects which are changing. Yeah. And they're more subtle than one they like, because these are log plots. This is a log number density here. This is a large fraction of your sample. So you actually change the samples. Depending on the cut you do, depending on your considerations, and depending on the redshift you probe, you're actually changing a lot the sample. Yeah? And this is nothing new. Yeah? And the amount you change the sample will depend on the galaxy formation model, or it will depend on the assumptions made. But in generally speaking, this is something to be aware of on how it changes. So, that you have your population is a changing membership of your stellar mass ranked samples. So, doing the evolution is not an easy one in that sense. Anyway, that was a digression. We just want to make that point clear because it's something which came up to me when we wrote the paper, that it wasn't at all obvious originally in the literature. Anyway, so back to MXXL. Okay, so we have a simple evolution where only the HOD mass parameters evolve. So that's what we've chosen to do, given the uncertainty of the other parameters. Note also that because we limit ourselves to lower redshifts, we actually can say, if you look back to these diagrams of the mass parameters, yeah, there's there's very little evolution in one of these parameters up to redshift 0.75 or even 1. They're pretty flat. So if you model this one first, and then the other one's rather flat, sorry, not this one, sorry, this is the one. This one here first as this linear relation, where these ones are pretty flat again, this is a broken parallel, you get actually quite a good measurement out. Okay, let's go down here. Then, okay, so now we know what galaxies we have in the sense of our HOD parameters. Now we need to think about the luminosity function. And there we actually take the luminosity function, a function of redshift from gamma, and such a way that we actually get we know what the luminosity of the object are different redshifts. Yeah? Because we want to create a HOD model with properties of these galaxies. Yeah? Then we follow a scheme written up by Skiba and Shet to actually to assign the galaxy colors, and we include there the evolution of the colors from gamma as well, because you can see that the galaxy colors evolve with redshift, so you can include that in the model. The end product, and I'm not going through this in detail because it's absolutely, I won't say boring, but it's very technical. Yeah, and I don't want to go into that. I want to give you the gist of the things. But unfortunately, 90% of the work is on these kind of things. Yeah, and it's just, which I've summarized. So end product is a line map with galaxies with positions, luminosities, colors that statistically satisfy many of the SDSS gamma constraints. Yeah. So the one which are directly constrained is the luminosity function. You can see here that these are the constraints we have. Is the dashed line, and this is what we measure in the MXXL simulation at the end of it that we have. Like our light cone, so its luminosity function works really well in the R band. Here's the clustering. The clustering by construction does very well. on the smaller scales, it does not perfectly well, and that we should go into the fact of how we model the radial distribution of satellites within the but in general speaking, it does very well there as well. You have the indirectly constrained properties, which is, for example, look at the correlation function as function of luminosity and color. So you have the red and blue galaxies, and that is, I say, indirectly constrained simply because we haven't used this data to actually constrain the model, but you actually end up with a rather good modeling, but not perfect. You can see here that the red galaxies don't have exactly the right clustering doesn't have the clustering with much perfectly data, so this improvement can be done. But we also have the luminosity, the redshift evolution of the clustering, which works really well. Here, in both sets of panels, now I need to say, the correlation function have been offset for clarity, because otherwise it will be all on top of each other, because you're talking about factors of 2 possibly to be changed in total between the lowest to the brightest one. And these are order of magnitude plots, so you need to offset them for visibility. But basically, this is kind of indirectly constrained properties which work well in the MXXL mark. So this BGS MXXL mark exists with magnitude limited sample of galaxies with properties from a cosmological volume with evolving dark matter density distribution. There's a main limitation on top of those kind of like model assumption I've mentioned in this discussion, is the MXXL mass resolution. See, the mass resolution of MXXL is not sufficient to have all the faintest galaxies that you can see in a survey like BGS at lowest redshift. So lower mass halos have to be added in as an unclustering sample of halos at the end. Yeah? Now, that is clearly unwanted, but there's nothing you can do if your starting point doesn't have those halos. Yeah? Well, you can try to be clever in how to assign the clustering of these halos, but they don't exist there in that sense. But implication is only affect the smallest redshift, really redshift below 0.05 and so on, where faint BGS galaxies can be expected to reside in 10 to 11 solar mass halos or smaller. Yeah? So it is really at a low redshift then. Now, so Alex Smith and Sean Call in Durham has put this together. Those who are in DESI have full access to it, but you can contact both of them to actually get, if you want to work with these marks. The next possible step, and Salman could not arrive into the room at the better stage, is why not do the same with outer rim? Because MXXL is just a low, it's a great simulation, but outer rim is just better on all aspects because it has higher mass resolution, more snapshots, and there was a third thing I don't remember now, and a better cosmology. Yes, that's what the thing. So, because the WMAP7, whereas WMAP1 for MXXL. And so this would have been, the technique is in there, so just making sure that one can actually put it in place to actually use on a different simulation. So that's a possible step. The other possible step is also add more DESI observables in a statistical way, because right now we're going to have colors and the magnitudes for the objects. And it would be nice possibly to see if we can add in more property, more color, more information, like some of the other bands that DESI will observe and so on for BGS. Okay, that was the MXXL marks part. Now I'm gonna go to the second part on this, and maybe I can ask if there are people who have questions at this time on the first part, because this is gonna be slightly, it's not different, but it's slightly different. It gives me also time to get some drink. Sorry?
What's the size of the box?
The MXXL box is 3 gigaparsecs aside. Yeah. For DESI, that is large enough, especially for at the low redshift survey, because you're going to have you go down to, you don't need any replication of the light cone until redshift 0.5, I think, which is pretty much where the BGS survey stops. There is replication done here just to make sure that you can actually do it and so on, but it's pretty much the right simulation volume in that sense. So actually it's ideal for that reason. The other reason why replication has been used is that the aim is to use this formalism afterwards to actually apply it to the LRGs and to the ELGs. Well, ELGs won't work because you don't resolve the right halos. ELGs reside in the halos that MXXL doesn't see to some level, 10 to the 11. That's typically where they're, and that's not possible. But you can do the quasars and so on. So LRGs and quasars could be done with this one out to a much higher redshifts. Yeah. So again, it's just working with this simulation, and then you can apply it to other simulations, but it's setting up the formalism of doing it. Any other question? Yep, sorry, yep.
Can you repeat again why you are not using the model that was affected the outer ring model?
Sorry?
Can you repeat why aren't you using the outer ring?
No, so the reason is not that we're not using outer rim, is that this simulation was available, sits on disks in Durham, yeah? And when you start a project, you don't know how big or how feasible things will do, yeah? So you start off with it, and you get away with it, and so on. I certainly think that now when you have actually created a mechanism for it, you should actually apply to outer rim, because it's an ideal situation to work on, you know? But when you develop, it's really hard to work remotely for certain things. You know, you want to, you know, having access to certain things is just practical. And I don't think actually it's possible to pass over, well, it might be possible to pass over the outer rim information. I'm not sure how easy it is to just do all of the information, or some analysis might just have to be done where they sit. Because it's the issue of the data, yeah. So if you can develop a mechanism of how to do it, then you have a pipeline, then you can transport the pipeline and then apply it locally where the data exists. Because in the end of the day, the light cone is not big, but the input to the light cone is huge. Because it's a 3 gigaparsec volume box with halos of down to a few 10 to the 10s and so on. In the case of outer rim, and you have all the snapshots in between, that just becomes a huge amount of data to work with. So, yeah. Okay, your last question, yeah, perfect, yeah, I'll do.
Did you already finish your talk? Or?
No. I have
I thought that.
No. I have. This is my second part of the talk.
I have a question for you.
Oh, that was mean. That. Okay, so let's go on now for the second part of the talk, which is about modeling galaxy surveys with HODs, and this is more about the HOD modeling aspect of it. And so what I want to say here is that to some level HODs, they have been and they are still tremendously successful way of describing and interpreting a galaxy population sampled by galaxy surveys. Yeah, they're very, very useful. But does it always work? And what is actually inferred? I think that's the thing to look into here. And this is just two short examples which I consider in the context of galaxy information models. Yeah. And so I'm just going to focus on the work of Contreras, which discussed the robustness galaxy clustering prediction, and some level about his other work also on the galaxy properties, which galaxy properties are correlated with the host halo mass, and then some work by Nuala McCullough to discuss the limitation of the HODs and in terms of observables, ignoring uncertainties in observables. Okay, so let's go back to now just a simulation with working in a snapshot level, so there's no light cone work, and we can look at the cumulative abundance of galaxies ranked by some property. Yeah, because at the end of the day, that is what you do when you look at HODs. You look at HODs, you take a property, you rank them in that order, and you say, okay, how will I model this sample? So you have here, just to give you an example of, we used here 5 different galaxy formation models, but basically there's 2 classes of them. There's like 2 Durham models and 3 Munich models. And the reason we did that is, again, to have more of a general feel for this, what is more generic. And to some level, we expect the Durham models to be more similar to each other because they're actually the same framework, gal form. And the same thing for the Munich models, the L galaxies, they're also more similar to each other. And therefore, it is useful to actually see that, is that happening? And actually, you see in most plots, you actually realize that this is really true, that there is a difference in the underlying model, like the family of models is the Durham or Munich models. So here we look at the cumulative abundance of galaxies, which have been ranked in this panel by stellar mass. Yeah? And the reason why this one is of interest is because most of these models have been tuned, and I say tuned to some level, to reproduce the stellar mass function. So the fact that they agree here is not a surprise. Yeah? To some level, that's the level of accuracy you would think that it could have been tuned to, that they are agreeing with each other because they have been set to work with the data, which looks somewhere like this. Yeah? But you can look at the same quantity as function of cold gas mass or even star formation rate. And then realize the simulations, the models are very different. You know? The two DER models are very, very similar to each other, probably quite logical again, and the three Munich models are also quite similar to each other. Yeah? And you can see these differences here. Now, the reason we have done this as function of rank name as function of these two different properties is we want to see, but what happens if you do HOD modeling on different properties more than just stellar mass and so on. And here is the density cut that we would apply, cut 3, 2, and 1, corresponding to different number densities of galaxies. And you will see these cuts coming through on a regular basis. Yeah. Now, if you look at the HOD, when you are ranked for density threshold samples ranked by stellar mass, what you get here in the top panel is all the HODs for these different scenarios. Yeah? So even though you had a very similar description of stellar mass function, there's no necessarily there doesn't need to be similar for the HODs of these samples. And you realize that there are differences. Actually, if you look carefully, there are actually very big differences here, which, you know, remember, this axis is 1, 2, 3, 4, 5, 6, 7, 8 order of magnitude. So if you see a difference on an 8 order of magnitude plot, it's rather significant. Yeah? You don't need to know how much it is, but it's significant. Yeah? And you can see these differences here coming in, yeah, between the models. And here you can see that the DER models and the Munich models are different in these terms for the stellar mass cuts. What will that have an impact? That will have an impact on the clustering. So a quantity which you can always estimate without having to measure the whole clustering is actually look at what is the contribution to the different galaxies to the clustering by using the bias of the halos they reside in. And you actually can plot therefore there, this is the kind of level, the contribution to the halos, the galaxies to different halos as a fractional contribution. And what you notice here is that despite these HODs looking very similar, a small difference, these contributions are maybe, you know, this is a bit different, but these are quite large differences here, and you have large differences here. And that's nice. I know that. That's purely from the model point of view. But is that what we measure in the data? No.
How do you
Yeah.
the bias?
The bias here, so in one sense it's an integral over I would probably write it up, it's probably easier to write it up like this. So it's an integral over the B of m, and then you have n of m, the number of halos of that mass, and then you have the number density of halos and bar of m h d of m, or probably d log m probably. So this gives you so this term here, and you integrate, so this is the contribution of the total bias, this is the effective bias of your sample. And what we have plotted, and you divide this by actually the integral of n of m n bar m h d log mh. And the reason you do this is so that you actually can see what is the contribution of the different samples. And here, what we plot the B of m is actually the part for which contribution each halo mass bin has in this estimate. And the nice thing with this is actually quite a quick way to actually have a feel of what is contributing to your clustering signal. If you look at these plots, like this HODs, you don't actually appreciate necessarily, where's my pointer gun? There's over here. The importance of the clustering from objects which are here. Yeah? Because actually, the unit line. Yeah? So in one sense, it's actually very important what you do in this regime to figure out what is the overall clustering of a sample. The other thing you don't realize when you look at an HOD like this is that you have a secondary peak coming up, which you expect because what is happening out here is you have the big halos, which have a very, very big bias. They're very strongly biased, the biggest halos. So they will contribute to your clustering signal. So it's a combination of those two terms which matters. And actually, if you look at the HOD, fitting your HOD to this, what if you really want to make sure the clustering is correct, you need to make sure you ensure that you get this part right and actually this part right. And this part in the middle is less important because it contributes less to your clustering amplitude. And the reason I was talking about this is because clustering is the one we actually go from to infer the properties, for a HOD model in the real data. This is simulation. I know everything. I don't need to go through the clustering. That's the big difference in this way. Now, seeing these trends here, what would you expect for your clustering? Do you expect that all these samples look very similar or not, or they're very different? And which one would be the most different or least different? Actually, it's actually quite, hard to realize that the one would be the largest variation, because this is the B of M, this has large variation there, actually has very little variation in your clustering signal. What does that tell you about? It tells you about degeneracies. Yeah. It's one sense, and the other part is that what you see biggest difference is only on small scales. Yeah. Note that this plot here, what we have plotted here is just R squared psi of R, just remove the main trend on the correlation function to see how these curves are varying with each other. And again, you can see that the models of the same family look very similar compared to the models of another family, generally speaking, and so on. But that's actually what these things are important. But remember, if you take the SDSS data and you infer clustering, you have the correlation function, and you try to infer the HOD. So that is something I want to remember on what is happening here. So what is the cause of these models being different to some level in your clustering? So you can look at the clustering statistics of all the galaxies, and I just took two models here, the Bauer and the Lucia, and look at the 1 and 2 halo term clustering, and for one of the density cuts. And you can see that the small scale clustering on Bauer and the Lucia differ, but on large scale it seems to be kind of similar. This is all galaxies, but only from the 1 halo term. That means that only galaxies which are living in the same halo has been measured the correlation function for. This is the correlation function of the 2 halo term, but between centrals, and this is all galaxies 2 halo term. And you can really see that they are very, very different between the models in this way, especially in this panel here. Yeah? And that's something which is important to remember, because that has an impact on where your galaxies actually how the galaxies live in your halos, and so on. And that's exactly what you can see here. This is the radius, the median radial distribution of satellites as function of halo mass for the different models. Yeah? And they're actually quite big differences here. Yeah? And then you have different galaxies, what they call type 1 and type 2, this is whether you have resolved subhalos or not, and that's the main difference in these cases, is actually a systematic difference here on the radial distribution. That's not a surprise, that's known to some level, because subhalos the clustering of the subhalos is slightly different to the clustering of dark matter, so that makes sense. And the type 1 and type 2 is one is actually just following dark matter, and the other one is following subhalos. So it all makes sense. Now, if you look at other properties, like cold gas mass and star formation rate, you end up with these type of HODs. They look, rather different. This is cold gas mass, and this is the star formation rate. Looks very different. And what is that an impact on is, can I actually infer this if I have a model? So first of all, I would need to know that this is the case, this is a true HOD, to infer the clustering of this sample. But it's not clear at all that you actually can make sure that you have a model which is generic enough, or you break your degeneracies when you're doing the clustering analysis, to make sure you can actually infer a HOD which looks more different. And the reason for this, again, is your HOD assumption comes in, you infer the type of model you have assumed. You will not, in any fitting, if you assume a functional form, you will just cover back the best functional form for that fit, for that functional assumption. Now, luckily, you don't tend to do star formation rates samples. That makes no sense to do it, because it's transient quantities. But that will have an impact on which properties you're looking at, different bands and so on, will have an impact of this. But if you look at the clustering, again, globally speaking on large scales, it's very similar, but all the differences in the models on small scales. Yeah. So, and then that's where it becomes actually quite important to how to do these analysis of what are you assuming for your HODs. And the reason for these HODs being different and so on is because the distribution of galaxy properties for sublunnar mass in these models, and this is like similar models, not exactly the same as before, is the Goert 11 and Lagos 12 models. You can see there's a lot of scatter in these stellar mass, and I can zoom into this plot. I'm going to zoom into this one, just make it easier. This is stellar mass versus subhalo mass, and this is cold gas mass versus subhalo mass. And you can realize that in the stellar mass one, the trend is kind of fine, kind of well behaved, and we have some scatter. And you have more scatter in the Lagos model, Dar model, than the Guo model, and that is one of the reasons why you end up having a poor description of the HOD functional form for the Lagos model of the Guo model. If you look at coalesced mass, the functional form is very, very, very different. You can realize here that actually, and this is the same idea of, in one sense, star formation rate, why that is an interesting one. ELGs in DESI, which emission line galaxies, are star forming galaxies. So if you go back to the plot here, star formation, that's maybe more likely to have a HOD of this type. Now, this is inferred from my galaxy formation model. I'm not saying that's the truth, but this is just an idea of how complicated you need to make your models to make them more realistic. Yeah. And you can see here, if you looked at the star formation rate, which is the bottom panel here, this is the star formation rate. You can see how these plots are very, very different in the two models. And that's normal because they're different galaxy model, but that also means that you may not be able to have a generic way of describing the HODs for those samples. Yeah. It doesn't remember what you put in and what you get out. So I think that's the message I want to give out here. Now this plot also, I like this one here. What we did here as well was looked at the resolution of the simulations, but using Millennium and Millennium 2 simulations. It's the same simulation, cosmology and so on, just that Millennium 2 has a factor of 50 higher mass resolution, but much smaller box. And you can therefore test how well your schemes have converged in terms of halo mass and so on. That's how we have split up these diagrams. But it gives you an idea of these stellar mass, halo mass relations or subhalo mass relations for your galaxies in the galaxy formation models. Now the last part, what I will consider, is clustering and HOD for luminosity ranked samples. And it's going back to a bit of this what I showed yesterday, this plot that I showed yesterday. In that sense, it's looking at what is the assumption we have made for making your HOD model and so on. So here is actually, so this just give you an idea of the background of the model is different simulation, different galaxy formation model because it's different cosmology, so slightly different. Sample ranked by luminosity, and we compare to SDSS data and HOD inferred models from Zehavi et al. Yeah. So this plot just shows you how well the galaxy formation model GalForm compares to SDSS. And you can see that to some broad extent it seems to be working well on large scales. Smaller scales, it's quite good, but it's not perfect. But it hasn't been tuned at all to do this. Yeah. Now, if I'm looking at this, I can also look at what is the HOD distribution for this luminosity ranked sample in my GalForm and compare it to the SDSS best fit of here. And you have the difference here is the solid line is GalForm and the dashed lines, there's like the dashed line is the SDSS ones. So a couple of things you notice. My clustering here is not completely crazy, but actually looks rather different in this parameter here. One of the things that actually I notice here in my galaxy formation model, I have a peak here. Yeah. Fine, that's nowhere near I could get that peak into my model. That's fine, but is that peak important? And what does it cost from? Maybe that's something relevant to ask. The other thing is also you can see that the HOD models, they don't plateau in the same sense in the case of GalForm as opposed to the models that are fitted to the data. I don't want to say GalForm is right, far from that. It's more the question of figuring out what are the limitations of this. And so here again we can do this integral and looking at the bias contribution in different terms for this. And if we can look at this one here, this one is the term under here is the numerator, and this is the denominator. No, numerator and denominator. Sorry, this is the numerator and this is the denominator. And this is the one that tells you about the bias of the terms. And this, in the case of GalForm, the solid lines, is the actual what you have what you actually have in the simulation, and you infer and you measure it. Whereas in the case of SDSS, this is what you infer the distribution from having done your modeling of the HOD. And you can see that these ones are actually rather different. you would have expected with these differences to actually see larger differences in the clustering. Yeah. Again, the clustering cannot break all the degeneracies that you have. And that's one of the things we need to remember. So to be truly honest, fully appreciate, you probably should always plot your HOD model with this scatter on its parameters. Yeah. But even then you realize it's not large enough, because actually here you have two models which are equally well fit. It's the dashed one and the dot dashed ones. They are equally good fits to the SDSS data. And they're quite different here, but you can't actually statistically differentiate between them. So actually there's large uncertainty on the HOD, which is inferred. Now if I'm looking here on this panel here, I look at a HOD again, and I can look now at what is the HOD for different galaxy types in the case of Galliform. And the reason, or galaxy colors. And the reason I'm doing this is because I wanted to figure out what is this object, but this is what is contributing to this. Yeah. So actually what you see here, that spike here is blue galaxies, and if you look at central satellites, it is primarily centrals. Yeah? Yes, primarily centrals. And that means that these are actually the result of, what you do in the model there. Anyway, so I'm just going to wrap up now on my summary here and mention that Lycon marks are important in many ways. They are needed because you need to properly interpret the observations. Yeah? And they are useful to test for systematics in the analysis pipeline. Then the Lycon marks, despite being built on rather general ground from simulations, because the simulations is run around ground, or if you have galaxy information model or a HOD, they're general. They're still very specific in the case of the Lycons, because the property and characteristics of interest for a Lycon mark depend on science goals that you have. Yeah? So you will not tune it in the same way, depending on, in one sense, you will tune it differently if its usage is going to be different. The size and accuracy of the Lycon is strongly influenced by the science goals as well. Because if you need something for BAO type scales, you need a very large simulation box. And that's, whereas if you want to galaxy information studies, you want to make sure you have the physics or the small scale behavior much more under control. And there's no method to populate simulation is perfect. All of them come with approximations and so on. But the key is determining what is needed for the science goals considered, and actually choose complementary methods in this way to actually make sure they actually get the best out of the strength of each of them, but also highlighting your weaknesses of all of them. And I think that's the point to do these different marks and so on. So yep, that's where I'm finishing off here. Questions? Aldo? You went the wrong direction.
Great talk. It's just a comment more than a question. So, I mean, this was a very good point about the limitations of HOD and the idea that if you constrain some luminosity sample, you are not putting constrained luminosity samples, no? So this will introduce all the inconsistencies that you showed. But one way to avoid that is just using another formalism, which is the conditional luminosity function formalism, and you will get a perfectly consistent sample, and that'll be all. Also, in the last sub-question on numbers.
But the conditional luminosity function formalism also introduce additional model assumptions in it. In the way you tend to actually assume the shape of luminosity functions and so on.
Yeah, but you have more constraints because you can now use the full luminosity function to constrain your samples, and not only the two-point correlation function. And the radial, and the two-point correlation. If you have only five points in the two-point correlation function, so then you have the covariance of the diagonal of the matrix, but also you have all these terms which are out of the diagonal, no? Which should be something like 5 for 5. I'm just putting an example of a correlation function with 5
Yeah.
points. So you are putting 1 point of the galaxy number density plus 25 points of the 2-point correlation function.
Oh, you mean the weighting of the two terms? Oh yeah. Oh, that's
actually you are basically omitting all the constraints from the number density. No, I mean it will be the same. Just neglecting the number density that.
No. So it's all. So the point you're making, and I fully agree with that point, is the issue when you're doing combination of data sets. How do you weight the two different data sets together? And normally you should not just add them together just as they are independent, or just giving similar weight. There is actually very complicated function to know how they are contributing. But more importantly, you also need to look at the covariances between those two data sets.
Right.
So
which is not usually done.
Oh, no, not at all. Not at all.
Yeah.
No.
Yeah. So that's why if you don't want to put everything and do it. I mean, taking all the covariances and all that. One way to avoid this is just to use the constraints.
Doesn't mean you have more points because you can actually. That's just it's just a way of weighting it. You're taking two functions and you just give a weight to one more than the other. You can apply that even if you have one data point. You can apply just a weight which is lower or higher. So it all comes down to how you combine data set and the statistics of it. And I certainly think for precision work, we need to work more on that.
Yeah.
But and I don't think there's a single. I don't think there's a quick method out of it, unfortunately.
Yeah, and just another comment about the matching number densities.
Yeah.
To get the evolution of galaxies using the stellar mass function.
Yeah.
So, I mean, people has been using a lot of this kind of inferences, but actually, I'm not expect that it's consistent with real evolution of galaxies. No. Just because it's based on the assumption that if galaxies are evolving just by star formation, they will just shift to the right in the mass function, and that's it.
But no, so no, I agree with that. But the point is, what I want to make is with this plot, I think that's the main point of what I'm making here. Where was it now? This one here, because that's one is just to have a feel of how big or what the trends are. And I think what for me was clear that there would be some fraction, but I hadn't appreciated that there's a that how broad that distribution can be, and all depends on this redshift range as well. So clearly, at the very small redshift range, it's not too bad. But actually, what is worse, it's even worse for the lower number density samples, which people actually have assumed to be a good ones to actually carry on with. And if I think about this, lower number density samples, I think LRGs. And LRGs is what people love to use these days in their cosmology surveys. So to interpret them is actually quite an issue for that reason. But this is illustrative. It's just, I'm not saying that there's nothing more than that. It's just, again, making people more aware of something which is a well-known fact, actually.
Further questions?
I have more questions. I will make more questions. If you don't ask questions now, I will ask questions about the project. Yeah. I've locked the doors. Yep.
You just finished.
I have finished, but I will ask, because I'm not here this afternoon, I will actually give some comment about project, because I thought that would be useful for those who want it in that sense. But if there's no questions as such, I can go in. Yeah?
So, the example that you give us is a magnitude.
Sorry, it's a magnitude limited sample, right?
Yeah.
Okay. So I'm guessing that in order to make the luminosity, the number of galaxies per luminosity, we should weight the sample, right? Like
that depends on how you define the sample.
Okay.
Yeah.
Okay. Thank you.
So that's So the weighting, it depends on how you do it. So it's like I was going to give just a couple of hints for that project. So for those who are working on a project, I'll do that. For those who haven't done the project or are not going to work on project, they can leave, in my opinion, in that sense. But I'm not gonna make sure, if I see too many people leave, then it's not good. But I'll more think about those who have other things and so on. But so I was gonna give this couple of quick comments about the project. So I thought it would be useful.
Maybe you
Yeah, maybe.
should remind the projects.
Yes,
Yeah.
that's what I'm going to do, because I'm going to put it up here. I have it there. There's the project. Okay, so the project is basically as follows. You have a survey which provides you a Galaxy catalog, and the Galaxy catalog lists certain properties on it, and one of the things I've asked is actually plot the differential number counts of Galaxy functional apparent magnitude and a plot of the redshift distribution of the sample. That shouldn't be very complicated. It's just pretty much just plotting x versus y and so on. But the more reason why I'm asking you to plot that, I'm asking, so to people of y, I've been asking you to plot that. The answer is because if you don't plot those quantities, you don't know whether it's a flux limited survey or not. As basic as that. And how do you realize this? Is because you actually, when you plot your number counts, what you will see is something like this: log n and r band. Something goes up like this. Yeah. So it gives you that you have more objects that they are as fainter magnitudes than you have at brighter magnitudes. And you put the n of z, you actually see something like this. dn, dz. Something goes up like this. And that tells you also that you have to deal with a magnitude limited survey. Now, the two terms here, that this one is sharp here, and that this one actually well behaved, is a very good indication that you just have a simple flux limit on a survey. Now, the other thing, as one says, is you're just measuring the luminosity function. How do you measure the luminosity function for a sample?
You have the magnitude, right? So now you have
Yep. So you can transform apparent magnitude to absolute magnitude. I'm just going to take them off here. You can actually do one plot, which is actually very useful once you have measured that. It's the following you can do. You can do absolute magnitude is simply the apparent magnitude minus 5 log dl, and then you have a 25 term because you have dl in h inverse megaparsec, and then you have minus k per z correction. Yeah, so you can actually do absolute magnitude. What the project can do, which would be very useful, is to plot absolute magnitude versus redshift. Because if you do this plot, what you will see is the following. You have a line here coming in, and you have data up here. That is really the way to make sure that you have a flux limited survey. Because now you actually see what the limiting magnitudes are for each of your survey. And what's happening here, this line here, is simply defining you the magnitude limit of the survey, R lim, which is the same values I had here, R lim. Yeah? That is defined. The limiting magnitude at any given redshift, what is the maximum or the brightness you have, that you get R lim is given by this relation where you replaced M by M lim, and you give you M max at that redshift. Okay, so once you've done that, then it's actually quite handy, because then you can create your luminosity function. How can you create your luminosity function?
You have to weight your galaxies, right? Giving more importance to those who are less likely to appear. And well, what I was thinking is considering the maximum, well, the magnitude in which you have your maximum.
Yeah.
As like, giving it a weight of 1, and then the ones that are lower, giving them higher weights. And once.
But what is the weight?
Okay, like if I have one galaxy that is really unlikely to appear, then counting it as if it were more galaxies.
Okay, but how would you measure that? So I'm going to give you a very quick answer here, because what you want to do is the Vmax, volume over which you can see it, but it's much, much easier than this. Because if I take a narrow redshift range, this here, the thing I can do, if I select all the objects in this box, see there's some small object not missing here. Those ones are volume limited. Yeah. And if you're volume limited, I do a histogram. And I've done the problem. Took me 2 minutes. But you needed to figure out the volume limited part of it. All of this is the thing. And here, if you use all of the galaxies out down here, you will have a bias for these objects coming in this diagram here, down here, because those ones are not viewed over the whole volume. So you actually solved very quickly question number 2, or 3 actually, I think. 3, and then afterwards you do the best fit. Best fit, check the function is a fitting. I think everybody can do fits. That's just statistics. And then you have to talk about what the errors are, you know, and I think that's not very complicated. But the point I want to come across is this issue of flux limited sample and making a very simple measurement for the volume from a volume limited sample to get a luminosity function estimate. And the problem with this one is just that you will just get a luminosity function over a very narrow range of luminosities because it's determined by this one and up to here. So you might just be able to see it on the bright end of it. But I didn't ask for the optimal one of the whole survey. So that's how to work it. The Vmax would require you to actually measure what's the maximum volume of a galaxy you can see. And that's require, it's not difficult, but it requires more coding. And so anyway, that was the project. Quick. Any questions? Wow, everybody seems to be happy. I'm glad for that. I think I'll.
What is the width in the redshift in order to determine a volume limited sample?
So the width, you can choose as wide as you want here, but you need to remember that why do you choose it? Here. All of these objects which are below this line,
you are missing them.
You should not use them because that will influence your luminosity function.
Yeah.
So what is happening is actually you can measure it for the whole sample, but you're just going to turn over because it's turning over. You haven't seen all the galaxies over the right volume.
They're missing.
Yeah, they're missing in that sense. They're not, you can't see this galaxy which is down here, you can't see over the whole volume.
Oh, okay.
Yeah. And the one thing I haven't, there's another thing, to just get the histogram right, you need normalization, you need to calculate the volume, that's just co-moving distances and on this, with the sphere, so that's not difficult either, and the solid angle of your survey.
Okay.
Yeah.
I was trying to perform the Vmax method, but now I realize that you only wanted to select a body.
No, you don't ask. I just wanted to give you an estimate. I want to give it as simple as possible.
Okay.
I'm friendly. I'm not somebody who wants the optimal estimator.
Okay.
I just want an estimate so that you think about it.
Okay.
As opposed to having the whole coding up and so on. And you're actually more likely with a Vmax to have coded something wrongly. Because what is the maximum volume of which you can see a galaxy? You need to determine that. So for this object here, it would be, I can see over this volume up to here. In that sense. So you need to measure that for each of the galaxies separately and so on. It's not difficult. No, I'm not saying that. It's just more, the more coding you do, the more chance you have to make errors. The other thing as well is, it's nice to know how to quickly get an answer which is correct, which is very basic, because then if you do the big complicated stuff, that should agree. So that is the other thing as well. Just give an idea of going quickly to an answer is actually very useful in research as opposed to get just always the precise answer. To have in a rough, what is the order of magnitude, and so on. And that will help you do this one as well.
I had another question.
Yeah.
And it's regarding the last point you made, that you gave us two samples, one
Yes.
deep and one is deeper than the other.
Yep.
And I plotted the luminosity.
Yep.
Actually, I made this plot.
This is the N of Z.
Yeah.
Yeah.
And no, the first one.
The first one. This one here.
This one.
Yep.
And well, I just thought that, well, combining both of the samples, you get like an extension,
Yeah.
because you're watching deeper and more luminous galaxies, so you're following this relation there.
So you will have a line which goes like this.
Yes.
No, this is the deeper survey going in here. Yeah.
So you were saying, well, you asked to think
Yeah.
how we could
Combine it,
this.
yeah.
So I thought that maybe doing this cut would solve the problem, isn't it? Or is there any kind of correction you have to
There
make?
is a subtlety. There's a couple of subtleties comes in. I don't remember now. Do the deeper survey contain galaxies of the fainter survey or the brighter survey?
Yeah.
I don't remember. So you need to make sure you don't double count. Classic. The other thing is the area the same?
Okay.
They're not.
No, actually,
not the same.
If
They're
it's
different
deeper,
areas.
it should be less the area that you're sampling.
You could have just made a deeper survey. There's just by construction, this one is a deeper survey, which is smaller, which is more common actually. And then you come into the way of how to combine the data sets, because actually, what is the volume you would see in a galaxy over?
Ah, okay.
It's actually different now,
Yeah, it's
because it's not
You
the
have
whole volume. Exactly, you have
to
to match them up exactly.
Okay.
Again,
That's true.
all of those small things, nothing is too complicated, but it's just all of these things one need to think about
Yeah.
and putting them together. I've on purpose made it simple to make sure that you only have one K correction, for example. But galaxies have different SEDs, therefore you should have different K corrections. And then all of what you do becomes much more complicated, because this line here, which is a straight line, is only a straight line because you have fixed K correction for all the galaxies. If there was different K corrections, you would have a fuzzy line, and then that would need to be accounted for. All of these things comes into the importance of where you can measure your luminosity function.
Thank
Okay?
you.
Yeah, you're welcome.
More questions? We have time.
Yeah?
Where's your accent from?
My accent. But it doesn't make the accent right. I think we'll wrap up if there's no more questions. Thank you very much.
Let's thank Peter for the whole
So,
Well, the food is expect to be ready at 1:30 or something. So you have 5 minutes break before going.